You ever look around and notice how certain patterns just repeat themselves all over the place? How things that seem totally different on the surface are actually playing by the same rules? Well, today we're going to pull back the curtain on one of those hidden connections, a universal blueprint that shows up in electronics, mechanics, even in our own bodies. Let's dive in. So let's start with a puzzle. What could possibly connect an electronic filter, a car's suspension system, and the way medicine works in your body? I mean, on the surface, absolutely nothing, right? One's about circuits, one's about springs and shocks, and the other is pure biology. They seem like they're from completely different worlds. But what if I told you they all march to the exact same beat? And that's the secret. That's the big reveal. Underneath all the specific stuff, the resistors, the springs, the body's enzymes, they are all what we call first-order systems. And here's the cool part. Once you understand this one blueprint, you suddenly have the key to understanding and predicting how all of them behave. All right, so what is this master blueprint? What does it actually look like? Well, it all boils down to one single, surprisingly simple equation that describes how these systems react when things change. Okay, here it is. Now, I know that phrase, first order, ordinary differential equation, sounds like a mouthful, but don't let it scare you. All it really means is we're looking at rates of change. And the equation itself, it's pretty straightforward when you break it down. Y is the output. That's the thing we're watching. U is the input. That's what we're doing to the system. And that dy dt part, that's just calculus speak for how fast is the output changing right now. So really, this equation is just saying that the system's current speed plus its current position is all being driven by whatever we're putting into it. That's it. Now, the real secret sauce here is that little Greek letter tau. This is the time constant, and it is, quite literally, everything. It's one single number that perfectly captures the system's entire personality. Think of it like this. A small tau means you've got a fast, snappy system that reacts right away. A large tau, that's a more slow, sluggish, kind of laid-back system. It's the system's DNA, all packed into one number. Okay, so we've got the theory down. Now for the fun part. Let's see this blueprint in action and check out how it actually builds all those different systems we talked about. This is where it really clicks. First up, let's look at something you'd find in basically any piece of electronics, the classic RC circuit. It's just a resistor and a capacitor. It's a fundamental building block for all sorts of things like filters and timers. And, you guessed it, it's a perfect first-order system. And would you look at that? It's our blueprint again, just wearing a different costume. The letters have changed to match the circuit, but the structure, it's identical. And that all-important time constant tau, for this circuit, it's just the resistance R multiplied by the capacitance C. Simple as that. Okay, let's jump out of the world of electronics and into the physical world of mechanics. Here we've got a simple model of a mass moving against some kind of friction or damper. You can think of it like a really basic car shock absorber or one of those things that keeps a door from slamming shut. And you know what's coming. The pattern holds. The time constant, tau, in this case, is just the mass, m, divided by the friction coefficient, b. It is the exact same mathematical structure. We're just plugging in different physical properties. All right, what about a tank of water filling up while it's also draining out the bottom? I mean, that's got to be different, right? We're talking about fluid dynamics, pressure, flow rates, a whole different ballgame. But nope. And hey, don't get bogged down by all the new symbols for density and gravity here. The crucial point, the big takeaway, is that the underlying equation describing the liquid's height, h, still follows that exact same blueprint we've been seeing all along. Its time constant is just determined by physical stuff like the tank's area. The pattern is just inescapable. And this is where it gets really wild. This pattern isn't just in the machines we build. It is literally inside our own bodies. In medicine, this is called first-order elimination, and it describes how tons of common drugs are cleared from your system. Basically, the faster your body clears the drug, the more of it is present. It's a perfect match for our model. So, knowing a system is first order is, well, it's like having a superpower. It means we don't just get to describe it, we can actually predict what it's going to do with amazing accuracy, all by using that one magic number, the time constant. So let's ask a really practical question. What happens when you actually do something to one of these systems? You know, you flip a switch, you step on the gas, you take a pill. In engineering, this is called a step response. And because all these systems share the same blueprint, they all respond in the exact same predictable way. They all trace out this beautiful classic exponential curve.
The output doesn't just snap instantly to its final value. Nope. It rises really fast at the beginning, and then it gracefully, gradually levels off as it gets closer to its final destination. And this simple little equation here describes that curve perfectly for every single one of those systems. All it depends on is our good friend tau, the time constant.
And this table here, this is awesome because it makes it super concrete. After exactly one time constant has passed, any of these systems will have reached 63.2% of where it's eventually going. After 3 time constants, it's 95% of the way there. And by the time you hit 4 time constants, or 4 tau, it's over 98% there. In fact, that's what engineers often call the settling time. For all practical purposes, it's done. So the time constant isn't just some abstract concept. It's a real, practical ruler you can use to measure the future. All right, so why do we care so much? Why does this one simple model matter? Well, because understanding this is basically step 1 to designing and controlling pretty much everything in the complex world around us.
So, look, this isn't just some neat math trick. It's a fundamental principle of how the physical world works. Here's the deep insight. Anytime you have a system with one main way to store energy, whether it's a capacitor storing electrical energy, a moving mass storing kinetic energy, or a tank storing potential energy with its water level, it will almost always behave like a first-order system. That's the powerful connection. And that is why this single blueprint lets us design everything from the filters in your phone to the timing of life-saving medication.
This quote from MIT OpenCourseware really nails why this whole idea is so revolutionary. The goal in science and engineering is to find that minimum set of variables you need to completely describe a system. And for all these incredibly different things we've looked at today, that minimum set was shockingly simple. Just one variable for the output and that one magic number, the time constant. That's the incredible power of a good model. Think of the first-order system as the first letter in the alphabet of how things change. It's simple, it's powerful, and it's absolutely everywhere. But it leaves us with a really exciting question to think about. If this one simple blueprint can unlock the behavior of so many different things, just imagine, what other secrets, what other more complex patterns are out there, just waiting for us to discover them?